So the last talk was a good motivation for this question. And some of the speakers yesterday, in the beginning of yesterday's session, raised a point I think that our community needs to be the one to address, which is with the advent of convolutional nets that are sweeping Google and Facebook and the rest of technology and that are very effective, at least for certain classes of problems. In the last 2 or 3 years, the question comes up in any debate with people in that community and in the outside community beyond either of ours, which is, can you show us how neural circuitry is more powerful? It's been a holy grail for 50 years. It was the impetus for artificial intelligence, neural networks, which are the what led to convolutional nets and hierarchical nets, somewhat neurally inspired. We believe that more neural systems will be more powerful, both in terms of not only size, weight, and power, but in terms of doing things that convolutional nets and their category cannot do. But we need to be able to show that. And if we don't, who would? So in that context, I wanted to pose the question during this talk of how would one systematically quantify a superiority of a neural system of some sort versus a machine learning system. It's not good enough anymore to assert that neural systems are powerful. Someone yesterday said that the existence proof of a hummingbird, it is an existence proof. But, we have to begin to build systems that are more powerful. How do we quantify that? Well, before I go through my framework for how I would suggest one way to quantify neural systems versus machine learning systems, I want to advocate for and what I'm going to use is a cortical system that's not the neocortex, and I wanted to briefly explain why. I've spent most of my research career simulating neurons and synapses in the neocortical circuits. My thesis was on the simulation of a thalamocortical column. So I'm the first one to want to understand the neocortex, but here is a picture of one of the great students of the neocortex, Alex Thompson's picture of just the excitatory connectivity. This is just in 2003. Of course, it's much more complicated 12 years later, and it's only the excitatory circuitry. So simply on the face of it, if one wants to understand neocortex at the circuit level and then build machines, build systems, build algorithms based on it, that's a complicated circuit to start with. Is there a simpler one? There's another issue, which is not just its complexity, but Jeremy Freeman earlier described new technologies that are emerging in the ability to image circuitry in vivo during sensory response. That is a transformational enabler of models of neocortex. It's never before been possible to image in three-dimensional volume the firing of all or most of the neurons in a region of cortex. Jacob's program will have that done in concert with serial EM to get the wiring as well. But here's a problem. This is neocortex. This is from the Allen Brain Atlas in mouse. It's a small brain, but still this is neocortex. And this is another cortex that's evolutionarily the predecessor of neocortex called Piriform, olfactory cortex. Is my mic not working? Is that better? Yeah. Okay. Thanks for telling me. So the depth here is about 1,200 microns, and that's less than you would normally think of because the mouse is small. Piriform is 500. Now, here's another advantage of Piriform. If you want to use Jeremy Freeman's method, you remember he showed you the layer 2-3 system in the barrel cortex of the mouse. That's just, the layer 2-3 system is just this part of the circuit up here. And there's all the rest of layers 4, 5, and 6, and the many excitatory and inhibitory neurons that are present there that complete the circuit. You can't really imagine simulating the entirety of the circuit with just observing activity in the top 40% of it. Whereas Piriform has the advantage that you can image using Jeremy's type of technology. You can image the entirety of the circuitry and observe it during sensory activity. So here in neocortex, you can only image this much of that circuit. And so it's really, in some respects, only going to benefit in a very limited way from the ability to observe the circuitry, because you can't see more than the top 40%. This is an image of mouse piriform cortex. Jeff Lichtman and Venki Murthy at Harvard were both responsible for this. This shows that you can stain individual cell types. This is a cell type that's like layer 4 cells in neocortex. It receives most of the feed-forward input. These are the output synapses of that cell type that relay the input. The entirety of this can be imaged. But the other advantage is the simplicity. So if you remember that circuit diagram that I showed you a moment before of neocortex, this is really the canonical circuit of piriform cortex from John Becker's work. I won't walk through it, at least not right yet. But it has a feed-forward circuit. This would be the analog to the layer 4 cell. And if you look at this and then compare this to the simplified canonical circuit of the neocortex, you can see a great many similarities. Very few. The main difference is the advent of layer 2-3. With this playing the role now of layer 4 cells that had been that green stain neuron in the image that I showed you. So piriform cortex is far simpler, order of magnitude simpler. It's shallower, so it can be visualized. And yet it's evolutionarily, at the circuit level, linked to neocortex. So that's my argument for why it's a smart place to start. I'll quickly show you one aspect of its computation. Obviously, short talk can't do justice to this. It's in the nature of invariant object representation. But here, instead of visual objects, we have olfactory objects. This is one odorant as concentration is changed by an order of magnitude, and its activity in the olfactory bulb, which you could think of like the thalamus and retina for olfaction. Yet, if you can see it, this is from a paper by Richard Axel 5 years ago. This is the activity using that same wide field two-photon imaging method. This is the activity in vivo during presentation of one odorant, and then the same odorant 5-fold higher in concentration. So even though the retina, if you will, the olfactory bulb in this case, is much more active at the higher concentration, you mysteriously have this sparse distributed representation. About 9 or 10% of the neurons are active here. That doesn't change, even though it's being driven by the olfactory bulb. So the piriform cortex and the circuitry around it achieves a sparse distributed representation that's odorant specific, that's invariant to changes in concentration. That kind of capability has a lot of relevance to coding in the hippocampus, coding in the higher stations of the ventral stream, the visual cortical hierarchy, sparse distributed representations that are object-specific and invariant to transformation. Okay, now back to the original premise. So I'm going to use olfactory cortex for this, but back to the original premise. How do you systematically quantify how a neural system might be superior in some setting to a machine learning system? Well, you need an environment, preferably a synthetic environment, a simulated environment, so that you can incrementally make the problem harder under control of parameterized levers. So you need some sort of simulated environment. Now you could use video data, but then you'd have to be able to incrementally make the problem harder in a way that's under your control. So here's a simulated environment for olfaction. This is a fluid dynamic simulation. On the upper right is the activity of 100 olfactory sensors, like the elements in the olfactory bulb. On the bottom right is the log of concentration. You see concentrations seesawing wildly as the agent goes through the system. In the middle of this is the fluid dynamic vector field that's being simulated that underlies the movement. The point here is that you see that the agent perturbs the vector field. So what we have here ultimately is a simulated environment that's suitable not only for sensory problems, the cocktail party problem, how do you determine what odorant is where, but also later sensory motor problems. To use this environment for sensory motor problems, you need to have the movement of the agent perturb the system. And we built a simulator that does that. So what is the sensory motor problem that we're going to start with? It's actually one that Jacob has sort of used as his canonical problem, and that's object recognition with multiple objects in a cluttered environment with backgrounds. You see that purple, that's a fifth odorant, that's the background odorant. You see its level right here is quite high and fixed. And it very much complicates the sensor activity. So that background activates sensors. You could be in a background that you never learned. So it becomes a tougher problem. How do you identify each of these odorants? How do you go find one when you're in a background that you've never experienced before? So we don't, in this system, we don't learn the background. Good travels, Jeff? No, not at all. So we train in one background. So this is training. I'm just showing this to indicate that training is taking place with the presentation of one odorant at a time. So that would be the period where the system, whether it's a machine learning or a neural system, can use the sensory pattern to learn the red odorant and then to learn the blue odorant and so forth. The test, so this would be then now to shift to, let's call this an olfactory spectrogram, in analogy to Lloyd's auditory spectrograms, where instead of multiple speakers, we're going to have multiple different odorants in the cocktail party environment. This is concentration. This is the activity in the sensor array. You see that there's background here. The background activates these sensors, and it's present all the time. Here's a different odorant. Here's a third odorant. Now here's all of them together. So the problem is, as the agent goes through, traverses the environment, it's going back and forth through the environment, the sensory problem, the fitness metric is going to be predict the concentration vector. An easier problem is what's the strongest odorant I'm smelling at one moment, but a more informative measure is what is the concentration vector at any one time, because you can smell more than one thing, and even though, you know, cheese might be the strongest smell, you want to be able to smell the cat that's nearby if you're a mouse, even if cheese is a stronger smell. So you got to be able to detect multiple things at one time. That's the nature of the cocktail party problem. And you see the difficulty. That's the pattern to the green odorant. That's everything together. Okay, so this, remember, was the olfactory canonical circuit. So let me walk you through the simulated neural system that we'll be using. I'll do this quickly, and I'll layer it mechanism by mechanism and circuit component by circuit component. So these would be the array of sensors. There's just a few here. This is a cartoon level simplification. There's 1,000 of these and 100 of these. And these are the feed-forward synapses. This is meant to indicate synaptic depression. In other words, the fact that these synapses, when active, become less effective. And that turns out, as you'll see later, to be vital. Feed-forward inhibition, somatic inhibition. Lateral excitation between these circuits, between these pyramidal cells. Feedback inhibition. Feed-forward dendritic inhibition. Now, another element in neural circuits that's ubiquitous, it's present in every neuron in the brain, is that the synapses and the neurons and the dendritic membrane adjust their excitability as a function of their activity. So there's homeostatic adjustment of excitability and synaptic efficacy that's universal and almost never incorporated, but really needs to be incorporated in synthetic neural systems. And it's not just these branches that homeostatically adjust, but these synapses and cell excitability as well. Now, these are not just elements of the canonical circuit, but they're also all mechanisms that are in fact present. And it's, of course, just a subset. So this looks perhaps like a complicated neural system, more complicated than a convolutional net, and yet it's a simplification of the olfactory circuit, which is itself much simpler than the neocortex. So the question then is how to systematically assess which of these mechanisms is central, and whether this circuit optimized is more effective than a machine learning system. I mean, that's what I'd like to say is our argument that a neural system will be more effective than a machine learning system. And that's the argument that I'd like to get to. For machine learning system, again, this is cartoon level in terms of number of units, but here we have a 4-layer net that's trained by stochastic gradient descent. So, you know, a well-familiar hierarchical net. One could use anything. So here's the performance of the 4-layer net. This is the actual odorant concentration for all 4 odorants as a function of time. This is the net's predicted concentration based on the sensor input as a function of time. What we're looking for is how well the normalized dot product of those two vectors match. So the normalized dot product of these 4 and these 4 values is this accuracy. And you see that it's pretty good. It looks like it's about 80% here. In fact, the actual accuracy here is integrated over the whole performance time is 71.5%. Well, before you can claim that either the neural or the machine learning system is superior to the other, you have to, in some principled way, optimize both, because we all know that you could screw up the parameters of one or the other system and make it perform poorly, and you've really proven nothing. So in the machine learning system, we optimized it with the 2 parameters that were available in this hierarchical net, the momentum and learning rate of the gradient descent. And so, as you can see, and this is for a 3-layer net, we got to 87% accuracy. That example was 71%, but we got it up to 87% accuracy in that normalized dot product measure of accuracy. And you see it begins to really asymptote in terms of these 2 variables here at about 85%. Adding another layer, so making it a 4-layer instead of a 3-layer system, just to see how deepening the hierarchy has an impact, doesn't really change accuracy much. It's 87% again. It's just more robust to different values of momentum and learning rate. And then finally, making that, adding more units. So in this case, 4 times more units doesn't change the accuracy. It makes it perhaps even yet more robust. In other words, it works at all different learning rates because there's more components and more power to the system in some respects. But the accuracy, as we've defined it, doesn't get any better than 88%. Now, let's turn to the neural system that I showed you before, that circuit that I walked through element by element. So that's a look at it again. And in order to predict accuracy, during the training period, we trained the simplest possible classifier. We have 4 readout units that receive the input from this array of, it's not 4, but this array of n neurons. And the synapses are trained or modified during training to basically form just a template. So the classifier is not an SVM at the back end of this neural system. It's just a template matching, the simplest possible nearest neighbor matching. And that 4-unit readout array is predicting odorant concentration. So what we have not done is we have not thrown machine learning horsepower on the back end of the neural system. We've simply used the neural system to generate the classification or the concentration prediction in the simplest possible way. To modify the parameters of the neural system, because there are a lot of parameters, as you can appreciate, we regularly use evolutionary search, evolutionary algorithms. So here we have 16 different parameters of this system: synaptic strengths, rate of depression, if any, homeostatic set points, in other words, levels of activity that are the homeostatic targets. So all of these different mechanisms can be evolved in concert and need to be evolved in concert to seek the optimization of this system. And also it's also a way to assess which mechanisms matter in the context of this performance as I've defined it. So I'm going to show you 3 results from the evolution process. It's really an interesting thing to study. I certainly can't do it justice here. This parameter is the integration time constant of the excitatory neurons in the system. So it starts out here at 1 time step. Well, I should first say that the fitness, the normalized dot product integrated over the performance time that was up to 0.88 for the 4-layer larger hierarchical net, or 87. Maybe this dashed line should be a couple ticks higher. So it clearly gets higher with the neural system. So the first point to make is that here's a case where the neural system, in a fairly tough problem, at least it appears to be a tough problem, this cocktail party problem in the presence of background, the neural system performed better than the 4-layer net in this example with these methods. It didn't start out better, but as you allow the parameters to evolve, it became better. And this is just 25 generations. It's really a very, one could evolve this much more substantially and have this continue to incrementally climb. But during the course of the evolution, you observe interesting things about what makes the neural system perform best. Here, the integration time starts out at 1, but the system evolves it to be around 8 or 9 time steps. So you get a benefit for an extended integration period in the excitatory units. You remember I showed you those pictures from Axel's work with the odorant at 2 different concentrations with a uniform level of sparsity. It was about 10% of the cells were active according to that paper. So here we start the homeostatic target. In other words, cells are adjusting themselves locally in order to hone to a target level of activity. We start that at 4%, and during the course of the optimization of fitness, that floats up to about 9.5%. So, interestingly, it comes very much in the same range as that example from the real Piriform Cortex. Doesn't necessarily prove more than that, but the point is that this parameter clearly has an effect on the fitness, clearly has an effect on the success of the neural system. And a system as complicated as this, you need some systematic way to optimize the parameters. The last result I'll show you, which is, I've got a paper in the works on this. It's a very robust result, which I can summarize as follows. If you have an object recognition problem in olfaction, if there's background, if there's changing odorant concentration, you must have synaptic depression. That synaptic depression that I showed at the beginning was a characteristic of the feed-forward synapse. So, meaning rapid, reversible reduction in efficacy that rapidly recovers. Starts out without depression, just because I wanted to start the evolution process without depression, and very rapidly, the very first thing that happens is depression evolves. That's responsible for the very first improvement in fitness. Happens every time. It's an interesting insight into the role of synaptic depression in enabling a neural system to function successfully. Okay, now some of you might very well say, and for good reason, that we haven't had Yoshua Bengio or Jeff Hinton tackle this problem. We just tackled it. So it might be that a deeper, broader convolutional net that's more skillfully applied could do better. And so in order to test that, I think the way to put these challenges out there is to build a neural system. Start with it doing better than a machine learning system, but then put it out there to the community. So we've posted this on TuneDit, which is like a Kaggle for the machine learning community that it should be at this URL right now. So, and maybe we'll put a prize on it so that you get grad students in, Eastern Europe and, just people that are not coming to our conferences but have free time and want to use their intelligence to earn a few dollars. And let's see if someone can do better. And so so if we challenge the machine learning community in this kind of crowdsourced way, well then what we'll do is we'll say, okay, they do much better. They'll send us the result. And we'll try to do, in this way we'll learn whether, and if they can't, then we've got a neural system that performs better than machine learning systems in a meaningful sensory problem. And let's go beyond sensory problems. Someone yesterday said that really it's sensory motor. I think Jeff said it's really sensory motor. So of course the simulated environment, you've got a little agent here that can be modified by that neural system I showed you to change its direction, in other words, you can have motor units and motor control units. So this can very straightforwardly be made into, we have made it into a sensory motor system. And maybe the problem is, find the blue thing in the presence of all kinds of other distractors, and eventually we'll find a problem that's hard. And what I hope and expect is that this will spur the further development of the neural system against the challenge of solving that yet harder problem. And I expect that eventually we'll find a hard, complex sensory problem in a real-world environment involving sensory motor control that the convolutional nets can't solve. And that's really, I think, the charge of our society, of our community, is to do exactly that. So that's my last slide, and thank you. I'll take your questions.
So I'll start off. So I really liked several things about what your approach is. First off, Piriform Cortex, having a more kind of tractable first step into Cortex. I like that quite a bit. And then I think this idea of having the comparison against conventional machine learning seems like a powerful approach. I mean, kind of a...
You have to, or else, there's 1,000 of them for every 2 of us, and they'll rightly say, well,
yeah, I mean,
show me something that we can't do.
The big issue, I suppose, and you kind of addressed at the end with the challenge, and when you were going over the 4-layer neural net versus your Piriform Cortex, and your Piriform Cortex clearly, from what I gather looking at it, and I imagine has feedback and thus has a time domain in its processing, whereas that feed-forward simple backprop network doesn't. And so do you have an intuition about, so clearly you're opening it up and you're kind of addressing that by letting people throw other methods at it, but do you have an intuition about, did the feedback nature of your Piriform Cortex give you an advantage in that?
No, it didn't. So it actually has a minimal feedback. Now, of course, we know that Piriform Cortex is embedded in the feed-forward feedback system with the olfactory bulb and the next Piriform Cortex area. So there is feedback in the system, but it wasn't included here except for feedback inhibition, not really area-to-area feedback. There are time constants in the system. There's time constant of homeostatic adjustment. There's time constants of neural integration of the different units. There's synaptic time constants. So there's a lot of temporal machinery in this system without substantial recursion. Of course, it would become more powerful if we extended it. And I would think that if we get into sensory motor problems that involve anticipation and prediction and actions based on prediction, then you may get to a state where you need meaningful recurrence.
Great talk.
Thank you.
Quick question. And or I guess first a comment is we actually did a similar thing where we had a toy model, and it was like a vision system, and we tuned it. And one of the things we tuned as well was the homeostatic base firing rate. We actually found it played a major role in our system as well, which I thought was a kind of...
You must work with Jeff.
That's right. That's right. So I thought that was pretty cool that you found it as well. That's kind of an interesting thing.
And it's no coincidence that in every neuron and synapse in the brain of every creature, there's homeostatic regulation of function of action, right? So it's got to be a neural computation. I think that makes it more likely than not that it should be ubiquitous in artificial neural computation. And then B, you have to have some way, and you guys use evolutionary algorithms as well. You have to have some way to have the system find the proper set points.
Right. And did you have plasticity? And if so, did you try to tune anything with that or no?
Well, So this system has plasticity only in the readout array.
Okay.
Right. So of course there's plasticity certainly in the lateral excitatory synapses. We didn't need it.
Okay. I see.
For this. It is there. There's wiring reorganization, something I talked about at this conference 2 years ago, in the sorting out of the wiring in the first place. That's important.
I see.
Right, that's not even there. So in a way, I would see this, even though it might have looked complicated to some, I would see this as a simplified square one.
Right, right. Cool, thank you.
So thank you again, Paul.